So there's a homework due on Monday that does some things with time series. So a number of the questions that are written there, so something like check the significance, check this. Well, that really means, look at it on the computer, output, and write a summary sentence or something about it. If you want to include some output to illustrate it, that's fine. Many of the things could be written as a shorter sentence. I found for working on different projects, often you put a lot of time and code into doing something, then it ends up being a short sentence or something that in there. But you have to have all that work to justify it and make sure it's right and things like that. There is a homework due there. The course finishes up with a second project and presentations. The presentations are during the final exam period, so there's Tuesday, December 10th, when our final would be scheduled. So we'll have presentations during that time. I think the final period is 2.5 hours, and given the size of our class, people can plan for up to 15 minutes to present, so you can present more on a data set, more on the analysis of things that you do, models that you check, and so on. So kind of the 10 to 15 minute range. So there's time to do that. The project, I haven't revised the project description, but it's much the same as the other one, with a preference toward using methods that are later in the class, multiple regression, more some of these variations on analysis of variance. We will look at things with repeated measures and categorical data. So if there are some survey data tends to have things that are yes/no responses, or responses in a few categories. Those things could be done as well. So the project tries to do a little bit more analysis, a little bit longer, but the same general idea. And so I'll try to write up something about that talks about that in a little more detail and get it to you, right? With the projects and presentations, as always, if you get it done a little bit early and want to submit a draft, I could look it over, maybe make some suggestions, things that you might check or be interesting, and so it can be an iterative process. Right? The thing that's coming up is Thanksgiving break as well, so that's the week before the last week. So choosing a project, getting data, so you're ready to go, at least a week before that, I think makes a lot of sense. If you're waiting to that break to get some things going and anything doesn't work, then you're kind of really crunched for time at the end. So we're going to spend one more day talking about correlation, time series type data, right? And we're going to look at a few more tests for autocorrelation, and then fit some models. So why so many tests for autocorrelation? Well, the tests are slightly different in what they do. People who work in mathematical statistics, it seems, and linear models with correlation, I think over time have really found that's something that they can do, come up with different tests, study their behaviors, and they understand that. Sometimes I feel that there's more tests than we really need for things, but they're out there, and people do make improvements from time to time. And it's also relevant to see if the tests agree with one another in terms of making a decision. So we have data, y1, y2, right, y sub n, time series or possibly correlated over time, so autocorrelated, correlated with itself. That you're going to do, and generally we have some x's. All right, so we're going to fit a model to predict, and maybe have many x's. It might be multiple. You also have time, right, as a potential variable recorded some way, and so we wanted to predict y from our x's, which could include. You might specifically include time as dimension there, and get the residuals. And many things like the analysis of variance models, our two-sample t-tests, our just linear regression assumes errors are independent. So are the residuals independent, or do they have some correlation structure? If they have a correlation structure, then the standard errors produced by the standard formulas, standard computer packages won't be right because they assume independence when they do their calculations. And so we have different ways of test this. We've looked at a couple. It's kind of a large sample normal test. So R1 is the first order autocorrelation in the sample. And if you take R1 times the square root of the sample size, the null hypothesis is, the parameter for that would be, or alpha is our autocorrelation parameter. First order autocorrelation, that it's 0, we'll reject H0 if the z value we get there is sufficiently large, 0, at a 0.05 significance level, right, if our z value is sufficiently big. And that would suggest to us that there is an autocorrelation. If the errors are independent, you'd expect z to be close to 0, and the bigger the sample size, you expect it close to 0. So that would be one way to test. But generally, because of the normality, it does work best if the sample size is large. A short series of 12 or 24 or something like that probably wouldn't be the best idea for that. There's a runs test that we talked about. So independence, you get positive and negative residuals switching back and forth without any pattern. But if they're autocorrelated, you tend to have some positive ones and then some negative ones and positive, and so you get a longer runs, but a smaller number total, right? So if positive autocorrelation, and there's two alphas, which is not the best, but anyway. Only so many letters in the Greek alphabet to use. I guess we need to learn to use a few more. If there's a positive autocorrelation, you tend to have a small number of runs in the positive negative of the residuals. So this one should work with smaller sample sizes instead of the requires big sample size. A graph you would typically look at with this, there's an autocorrelation function that's useful to look at, right? That would show the size of that and how it decays. And there's that non-parametric runs test, so-called non-parametric, it doesn't really matter what that is, but there are other tests that are done, right? One that you would likely see in the linear regression context is called a Durbin-Watson test. Test of a lag1 correlation. And so its statistic, D, is a sum over time of the difference of the residuals squared over the sum of these E sub t's of the residuals squared. And this one numerically ends up being equivalent to 2 times 1 minus R1. Right? But it's scaled so that this thing is between 0 and 4. And D equals 2 happens if the lag 1 correlation is 0. So this test exists because some people figured out, kind of independent of other normal tests, that this had a certain distribution, and they could enumerate it and come up with p-values. So it's kind of testing the same thing as the other ones, but slightly different, evaluation. So if you're working in linear regression, you're more likely to see this one, I think, because it's written up in more of the textbooks than that normal test or maybe the runs test. But anyway, this one would also be done. But there's a few other tests that try to look at things beyond the the first order of lag, right? Because you might depend, the first dependence on the first lag, right? Dependence on the previous one, right? The next one depends on the one that just came, kind of induces some dependence that goes longer, right? So if the first one affects the second, and the second one affects the third, and the third one affects the fourth, well, the first one is affecting these longer ones too, kind of through that structure. So there's a real high correlation. For every time period, you would see a correlation that goes longer, but it might be really created by just the immediate predecessor, right? So longer lags, but there could be a special correlation, like at month 12 or something like that. If there's a yearly effect, right, there could be this longer impacts. One way to see this is called a partial autocorrelation function. Right. And so what this will do is it computes an autocorrelation, correlation with a certain lag, and let's say lag k. So it's looking at y sub t versus y sub t minus k. What was it 2 ago or 5 ago or whatever k is, taking out the impact of lower order correlations. How could you do this? Well, you could take the current time, you could regress the current time point on a bunch of previous ones and take residuals. Right? And so what's left over is kind of the residual of the series, adjusting for those. This graph is shown in a graph and also a value. So we'll look at some pictures. And so the autocorrelation function might show very high autocorrelations that are all induced by the first one being really big. But once you take that out, this adjustment, right, can show you residuals that there's not a second or not a third. Sometimes there is, that they be higher order ones. Right? So this particular graph and this numerical thing, there are two other tests there that are mentioned in the literature. There's one called Broich-Godfrey test. And so the null hypothesis of this thing tests is that there's no serial or autocorrelation up to some order, up to order k. So that you run a regression up to a certain number of predictors of the residuals, and it tests whether those and gives a, so there is a serial correlation. Right. So we're not going to go into the details of what it's doing exactly. You could study this literature or look up other things. But I'm just pointing out that this test is designed to look at the longer term structure. right? And we'll look at an example of using it. There's a couple other tests that are similar tests, right? Young Box, and Box-Pierce. So George Box is the same person. They developed a couple tests in time series in economics, about a decade apart. So both of them are used there, and it's testing whether the series are independent or not. The statistic this one uses depends on how many lags you use, right? And it has the sample sizes in here of the length of the runs. And then the lags go from 1 up to h, and this R sub k is the kth autocorrelation. So it's a function of correlations up to, in this case, lag k. So this null hypothesis that it's testing is there's independence in the residuals up to lag h, versus an alternative that they're not independent. And so if there's a seasonal effect, right, but no first order effect so much, this could be. So there's different things that have been designed for looking at longer term dependencies, multivariate dependencies. And so it's really kind of a rich world in time series of looking at these things. But what I wanted to do, rather than go into details, I mean, if you go on and time series and economic data or weather data or something that's going to be really important to you, these things might be mentioned in papers, or you might learn more details about how they actually work and what their limitations are and things like that. So, but I thought we'd look at some data, try some of these out, try out some modeling, and see. And I'm going to try to switch over to my laptop, because some of these things are in packages. And so instead of just showing you the output, we'll see. Yay, good. Okay. So in my office, I loaded the packages, and so hopefully this should all work. At the top of this is kind of a summary. We're going to fit models, test autocorrelation on the residuals. If yes, we would do the filtering to redo the significance testing, or we do some other type of modeling with time series software, something with sines and cosines, something with a package that fits an autoregressive model, and so on. But anyway, this is a little bit of summary of some of these procedures. Some of them, right, you just do. Some of them want the residuals put in there. A few others of these packages require that you put a model in there. So it wants the regression model statement and so on, and you just kind of have to keep track of what it wants. All of these commands, like this Durbin-Watson DWT test, have help files. So if you do help of DWT, it will tell you what it does and give you a few examples, and so on. So let's go. So I've loaded these, installed these packages before, and I've typed library, and so they're actively being used in R. First data set is going to be this Nile data set that's invaded with R. It's measurements of annual flows of the river Nile at the Aswan Dam in 10 to the 8th cubic meters. That seems like a big amount. Here's a plot of the series, right? A little more jagged, but kind of, some dependence. It kind of goes high for a while, and possibly there's some autocorrelation there. It's not quite as definite as a pure seasonal effect. There's also something else, right, that there's a couple descriptions of this says that between these two time periods, a change happened. Right? You see the change? Right? So damming the Nile was a big thing. It enabled agriculture to be more stable. It stopped flooding. So in terms of the development of society, it was huge, civilization. Right? But this is more modern. Right? So we're going to have that length. We're going to put year in as a predictor. All right? So I'm going to make a year variable and fit a model that just has a change point. Right? Why am I doing a change point? I'm looking at it. It was also written into the file, so it gave me some idea of this. So let's look at what a change point might do. So I'm going to fit that model and then put the plot with the fitted values. Right? So there's the fitted values. Right? So this indicator is the year less than 1899. Right? So before 1899, you get one, and then after 1899, you get another. It's worthwhile looking at the summary of a model like that. Right? So the intercept is 849, about 850. And before 1899, you add 248 10 to the 8th cubic meters, right, to the volume. Right? So this seems to fit up here, and this seems to fit here. Without that, there's going to be a big autocorrelation, right? Because it's high and then it's low. That's a pretty strong pattern. So if you don't take out that pattern and try to test for autocorrelations, you're going to see an autocorrelation. It doesn't mean that you necessarily need it. The dominant feature is this real change point. Right? So what's the autocorrelation function look like for the Nile? Strong first autocorrelation, and then it keeps going. But if you do the residuals, is it there? Is there a pattern in the residuals once you take out that change point? This is kind of the barrier for the test, or the normal test, and so it doesn't appear to be there. Yeah.
Just to go over it again, like what are we looking for if in our residual plots and we're trying to figure out like if it's an autoregressive structure? Are we looking for if there's like an equal amount, like it's kind of like reflecting over the x-axis like equally, like?
Well, so generally the residuals, right, will be half above zero, half below zero. Not exactly. They add up to zero, but you get about half and half. Right? And so you're looking for kind of a sticky pattern, that if you put the residuals in some order, like a time sequence order, and if they're organized in the data set that way, then it's just the order of the data set, right? That you tend to have large ones and then small ones, and that the ones that, each time period, each one you see kind of tells you about its neighbors, right? That it's not completely random scatter like you would have, right? So if things are unrelated, and once we take out the pattern of the high-low, like they switch to something on the dam, right? And it doesn't, there's enough difference between years, right? That the flooding in one year doesn't necessarily affect the flooding in the next year. If it's separate enough environmentally, then, and how they process the water through all that, then where there's high one year won't make it high the next year. If that's independent, then there's not this autocorrelation. And it appears, once you take out these are the residuals, that it doesn't appear that there's much of a pattern over time. Right? So taking out that. The partial autocorrelation function is there's a PACF, right? And so this would say, the second one, they're going to change, right? The first one will be the same. But the second one will be, after you take out the effect of the first one, what happens? So if there's only a one-year dependency, these would tend to just be wiped out and be small. They're already small, so it doesn't make much difference here, but they would kind of wipe it out. So partial ones, see the first one is just, it's not quite significant, and then the other ones just kind of drop out. There. We can look at the residuals. Now the residuals by itself, right, if we just plot the fitted of the model, and mod, and the residuals from the model, kind of look like, well, that's kind of funny. Oh, no, that's not funny, because we only have two predictions, right? So that doesn't really tell us anything about the time structure, right? These are the fitted values, high versus low, so you kind of get these two fitted values. But if you just plot the residuals versus the model, it does it in time sequence. Right? the default plot doesn't put lines there, connecting them. The TS plot is a special plotting function of that does connect them over time. And do you see, this one, there wasn't much of an autocorrelation, so it's, it's just kind of moving up and down more randomly. If we do some of these tests, the first order autocorrelation is 0.5. Well, that's for the Nile, right? That's for the sequence itself. That's high because there's a high level and then a low level for a long time, right? But if you do the residuals, after you adjust for that, it's quite small, like 0.16. And the t-test for the Nile would be significant, but the normal test for the residuals, the p-value is 0.11. So it suggests that there's not a significant autocorrelation. The runs test, right, is just included with the default of R, and also gives you a p-value of 0.16. That's consistent. There's not strong evidence. The D1, the Durbin-Watson test, right, was in one of those packages, so I got that library of that package, and so that's worked. The DWT test had a p-value of 0.07. There's a Box test. This is the Box-Leung test, so these things have help files once you do the package. So it does these two couple test statistics, examining a null hypothesis of independence in a given time series. Right? Portman-2 tests are kind of composite tests. Any deviation from that. There's a couple options that are here. Where are those things coming from? If you look further down in the help, in the description here, right, it cites a couple articles in Biometrica and this one, and Journal of American Statistical Association, right, where George Boggs, with students or collaborators, came up with these and evaluated them and published an article saying you can do this test. Right? Modern versions of these things would probably have an R package built with it so that anybody could just kind of do it quickly without having to program it. But in the old days, you had to program it for yourself, right? Or get code. And so then these are included, I guess, in some textbooks. Right? But that's why there's two of them there. And, anyway, it's all consistent. This Broich-Godfrey test for serial correlation up to order 1 also is kind of this similar p-value. Everything's consistent. So it looks like if you get that change point right in the level of the dam, that year-to-year variation does not seem overly correlated. Right? If something happened where big rains 1 year caused floods and more volume for 2 years, and then dryness caused low levels for 2 or 3 years, and you would get more runs like that, then you probably would have autocorrelation. But it doesn't seem to come through. So that simple model seems to work all right. Any questions about? I think if you try to do a linear function of, what would a linear function of time do in this case? A linear function actually of going back to the original data. Back here a little bit. If you try to do a linear function, it's going to get some line kind of going like this. Because it has to be high up here and low here. So you're going to get some negative slope. It might be significant, but it might not work as well. And in situations where you know that they've done something, like they've intervened in the system and caused a change, that would be a good candidate there. Another area tries to detect that without knowing that information. Right? You have a series, and has there been a change? So change point problems are tricky because you don't know where it is, and that affects everything. So I want to look at the second one here, and that's the air quality and the wind variable. Right? And so there's 100 measurements of wind in New York City in 1977. Here's a plot of wind. Is there a trend over time? in the wind over this period, and it's about a 3-month period. Doesn't look like it's particularly going up or down a little bit, but it looks a little bit lower over here, doesn't it, right? Is it autocorrelated? Well, there kind of seems to be possibly, but let's investigate it, right? To fit a time, we need these are just listed as time. There are dates associated with them. You could do something fancy to try to put dates into there. But I'm just going to do 1 to n, right? And we're going to try time and time squared. Start with that, right? And so if you do that and summarize it, it turns out that both time and the square of time are significant predictors of this pattern. And you can work to do a little graph of that. R squared is only 0.09, so it's not real high. But if you put the fitted values there, right, there's a plot of the fitted values, that there's kind of a quadratic that seems to fit there, a little bit better than just a straight line. Right? And both of the coefficients, okay, well, this one is positive and negative, so it's the square, on the square, it's sloping up, right? So it gives that picture. Is there autocorrelation in the residuals? Do we have a plot? We did not do, let's do a TS plot of the residuals from this one and see, do we think there's going to be much of a autocorrelation? Well, they kind of go high for a while, then low. You know, maybe you can see something there. There's always kind of a judgment call. It's partly based on experience. If you do the autocorrelation function, yeah, the first autocorrelation looks a little bit bigger. The partial, is there seconds and more? The partial one, the first one's big, and then after that it's small. Generally, you kind of go up to the point that you see something not significant, and you don't worry about things that are long. So a big lag that's at 12, maybe there's a yearly, no, not 12, these are monthly, so yeah, I think my understanding or thought about these is that after you have some non-significant ones, unless you know that there's a seasonal pattern, that it's a little bit more noise, right? It's kind of fitting higher order models to the sequence. And you might find something, but mostly you concentrate on the lower orders because that's most of the story, right? The normality test would reject small p-value. The runs test, however, does not come up with a small p-value on the residuals. So for some reason, these two tests seem to give a discrepancy, right? Here's the picture, the time series plot of the residuals again, right? The normality test is based on bigger samples. We have 100 here, 100 residuals. Is that enough for normality to work out so well? The runs test says, well, it's not as clear. Maybe there's not a significant correlation. The runs test, did that make a little plot? Let me see. Help runs dot test. Does it have a plot option? Yes, it does. Let's do that. Plot equals true. And then we'll run that thing. Okay. That's the anyway, yeah, so I mean, there's 100 points, and it has the negative ones and the positive runs. And this is where they...
Where each run starts and stops.
Yeah, where each run starts and stops in there. So it's moving back and forth pretty fast. This is at the median, so it's a little bit below 0. So I guess that's enough of a shift back and forth to look like random to the runs test. Yeah.
So when we're looking at the p-value for these residuals, like if we get a significant p-value, just to clarify, we are rejecting that it's autocorrelated?
Oh, we're rejecting independence.
Independence, okay,
Yeah.
so we're assuming it's autocorrelated.
Yeah.
Okay.
Yeah.
All right.
So like in the normal one, it's R1 times the square root of n. So if R1 is big enough, you get a big z value. and you reject, R1 of 0 would be independent.
Okay.
So anyway, this one's moving back and forth, so that would be kind of an explanation of why the runs test is not saying, oh, you don't have a small number of runs, you actually have a lot, which is more like independence. So maybe that's why we have more multiple tests. The box test, gives a p-value that's not significant. That's consistent with runs. This Broish one, though, is more consistent with the normal test. Maybe there's some connection in terms of assumptions or something that is doing. And then the Durbin-Watson test, which is based on R1, and kind of like the normal one, also gives a small p-value. So what's the conclusion is, it seems like there seems to be some autocorrelation there by many of the tests, but it doesn't really show up in the pattern of runs, because it's maybe because it's weaker ones, it doesn't kind of come through. So it's a little bit fuzzy. I'm not sure what to come down on one side or another, but yeah, we might try other models. What if we add a third, right? So we had that nice plot back over here, right? Does this one dip down far enough? Maybe we should do something else. We add a third term, what do we get? Well, if we run the third term, suddenly everything is not significant, right? So adding time squared, and time cubed causes a problem, right? This is the multicollinearity, right? That the correlation between time and the square and things like that. I did a little effort there to get some correlations. These things, so time squared, and time cubed is here, right? Time and time squared has a correlation 0.97. Time and time cubed 0.91. Time squared, time cubed almost 0.99. And so altogether, those three versions of time are highly correlated with one another. So you put them all into the regression, and a computation goes haywire. A matrix can't be inverted very well, right? So the suggestion is to take at least some of these variables and take time minus the mean and cube that, right? Center it so that it's not. And if you center the time, the cubic one, the correlations to time and time squared go down. Well, yeah, they go down to particularly the time squared versus time cubed. So you really should take those out. So if you do that one, right, this model here, that's up here, the time and time squared are still significant. If you look back, the coefficients and standard errors aren't changed much from what was before. And the cubed one is not significant, so it doesn't look like we actually need it. But to test that and be kind of convinced of it, this made more sense than trying to just put it in straight as a cube variable. Same conclusion, but just better practice to try to avoid highly correlated predictors. So over those 3 months, the wind seems to be changing, kind of on an average thing. So maybe some evidence of some autocorrelation, but it's a little ambiguous based on the tests. I guess if you wanted to predict things over time, you could look at how it performs. An autocorrelation, you have this model, what do you predict for next year? Is it, or you say you take half this series and then do predictions? Are you going to get a better predictions with autocorrelation or without? So you might do some more further validation, right? Take this part of the sequence, can you predict out here? Or you take this part of the sequence, can you predict out here? Can you go another month out? Do autocorrelations help you or not, right? So it can be you can still evaluate beyond those particular tests to fit your data. One more example, right? The Mauna Loa CO2. It has 460 observations of atmospheric carbon dioxide at volcano Mauna Loa in Hawaii. Right? And since the 1960s, you see the huge increase in atmospheric CO2, along with the seasonal variation. Right? The northern hemisphere, affected by the dying winter, and then the trees dying off and releasing carbon dioxide, and then them growing and absorbing it up. Right? That's 468. So would there be an autocorrelation? Yeah, this has a huge autocorrelation just as it is, because there's this enormous trend. So we take out the trend and try to deal with other things. So we're going to set up a time variable. You could start it at 1960 or 1950 something and do fractional things like that. I just did 1 to 468 as the time, right? So it's kind of different ways of putting time in there. And so the model has, obviously a hugely significant time effect. The R squared for time alone is 0.97, so that's huge. The ACF function of the residuals has big autocorrelations, right? Because there's that seasonal pattern. Right? After you take out the trend, there's a huge seasonal pattern. And so the first autocorrelation is, 8 something, 0.8 something. And then just looking at the autocorrelations without adjustment, is the next few are very significant as well. So the partial autocorrelation would be useful, right? So is the sequence, does it just depend on the previous one, or is there a longer term dependence? And the partial would be used for that one. Right? This is the partial. So the first one is still about the 0.8, right? The second partial there is really low, right? So after you take out the impact of the first one, there's kind of a slightly longer sequence where things are reversing, right? And then there's a few more that, so 2, 3, 4, you might have captured most of the dependence by, like 4. 4 is probably enough to get around a curve, on that, right? So you might have coefficients up to 4. Some of these that come, that it's not significant. Some of these that come up, maybe that you would have some benefit from a yearly variation because of the nature. So there's some sine cosine thing going on in there. So let's put the square of time in there. Right? Both are significant, and I wanted to use the time, not my 1 to n plots, right, 1 to 468. I want the time of the CO2, because my plot of CO2 has that on there. So I did a help of the time series of TM, right, because that CO2 is stored there. And somewhere, going through down here, page down, it describes a time series. And then it has a few other commands that are kind of often used with this, right? Start and time. And so time returns the time scale on which the objects are there. So sometimes you can find useful things. Should you use print? Should you use summary? Should you use plot? How should you get information out of these R objects? So, yeah, time. So when I do this plot, I'm going to add the fitted lines from the couple of models. So there's the red one is linear, and the blue one has the square. Right? So the blue one is the curvy one. And so there's a little pattern there. A little deviation in the middle, right? And so that's kind of, the blue one suggests acceleration. Right? How about time cubed? Right? The cubic is also significant. We have 468 observations. These measurements of significance are not taking adjustment for the fact that there's not a correlation in residuals, possibly, so they might not be exactly accurate, but those are pretty small p-values. Even if the standard error is doubled or tripled or quadrupled, you probably still have significant. The fourth effect wasn't significant, so let's stop with that. The third one is a purple, well, not green now. Right? And so the green one's kind of in the middle of those, right? The cubic. Right? So kind of, it doesn't look like it's much change, but it's a little bit of change. And predicting out 150 years, those things will separate. The coefficient on the third coefficient is negative. Well, that's the summary mod 3, that one. the coefficient on the cubic term is, so eventually this thing is gonna come back down somewhere. It might not come back down, you know, kind of, it's going up pretty fast, so eventually it'll come down, but maybe not for 1,000,000 years, but that's the nature of the curve. I was just trying to extrapolate a little bit, so I'm gonna set up a plot. Here's the points for the actual one. You can do predictions with time series. So here's the fitted model. You can do predictions with time series, just with linear models, giving it new data. The thing that, you know, what the little thing is, like the x values have to be on this 1 to n scale. So you could add 600, right? So that's adding 50 years, or adding 100 years out from the data. Maybe it's not the best thing to extrapolate that far. But I have to use this measurement of time to make it work on this graph. So you just get little things to play around with. And so if you do that, where do the predictions go? Here's the predictions under the model. It looks a little funny. I think, you know, I probably would do something to make it, if I just kind of did the whole thing out there. But maybe it's just copying this pattern over here, putting it out there. Anyway, how do the other models affect prediction? I'm changing now from the model, that's the cubic model, and then the cubic quadratic, here's the quadratic fits. Look a little bit different, and then this one with just the linear is the red. Okay. So the cubic that has the third order seems to be a little bit higher. So it makes a little bit difference spreading out. You also can get standard errors. What should we do to model this with, you know, now that we have time cubed, what do the partial residuals look like? Well, it looks like the first and second one are significant, so maybe there's a first and second order thing on those residuals. So as we add more to the model, the residuals seem a little bit less correlated. And I was trying to look at these different tests, like there's this box tests for how many residuals, and they all end up being significant. So I don't, same thing for the Broich one. So I'm not an expert on time series, so I don't know exactly what's going on. The Durbin-Watson tests, a lot of those are for different lags. You can test for different lags, end up being significant. The time series plot for the residuals, if you look at that, it's just going up, down rapidly. There's this definite seasonal variation that we haven't captured. So all of these different tests for some autocorrelation really are significant. Right? Basically, I think they're pointing to that just a linear model is inadequate. That there's really this up and down thing. Right? So what people really would do in time series is try to decompose the main effect, right, which is seasonal, and then look at the residual. You would do something better than an ordinary linear model. There's a command called STL. It was included in the time series plot thing. STL is, we're going to look at seasonal trend. And what this thing does is it gives you three things. The top of it. There it is. It is decomposing it into a seasonal trend. Well, it's a trend, right, going up, and then a seasonal thing. See, there's minus at January, and then if you can see the next. The next January is a similar minus thing, and then residuals, it decomposes it into kind of these three things. And it uses something called low-S smoothing, so it uses another criteria to try to piece these things out. And if you plot that, you know, it gets the trend going up, which we're kind of doing with our modeling. The seasonal pattern, and this is seasonal, these are the data. And then the remainder, kind of the extra residuals. Maybe after you take out the seasonal, the remainder here looks more random. Right? So there's other commands that do something a little bit more than start with a linear model command to do that. There's a command called AR for autoregressive. So instead of saying that it just is one step, you can have models, and I think it actually gives it here in a little notation, that the current time period can depend on the previous one, the next one, and the next one down to the previous one. So you can have the current time period depend on a whole bunch of other ones. And so it can be autoregressive on several of these. And so AR fits that. You can tell it how many orders to have. This one kind of says it needs to go back to 19 previous measurements to get a good model to fit. It's choosing this with the AIC criteria, so it fits with 1 lag, 2 lags, 3 lags, and more, and then it stops at 19. You can save that, and it has a, if you use predict of this AR model does predictions, right? Going out. And the predictions are, there's enough coefficients in there to say it to model that up and down curve so that it models the up and down curves. There's a trend and a seasonality, and so for some reason I would think it would spread out because it would be more, well, I don't know, it's kind of maybe regressing to the mean or something like that. But it chose that model based on AIC criteria. So here's the AIC criterions for, no autoregressive, 1 order, 2 order, 3 order, 4 order. And so you see that at some places it doesn't drop very much. But you add the right term, and it drops more. And so this thing keeps going down until it hits about, this 19. It says it's 0, which I don't believe it's really 0, but it must be enough to get really close, right? But that's AIC. Right? AIC had a smaller penalty for more parameters. You could adjust that, right? AIC had 2 times the number of parameters as a penalty. Right? So each of these models adds, start with 1 parameter for the mean, another parameter for autoregressive, and things like that. So if you take out that penalty, you could add in what would be BIC. Right? The log of n is going to be the penalty by log of 468 is a lot bigger than 2. Right? So if you do add that back in and look, kind of adjust that for BIC, you get a little different picture where you're going to stop at about, which is the smallest. So 13 ends up being the smallest lag, right? Just over a year lag, right, would be suggested. So maybe you can get by with a smaller model and still get almost all the seasonal variation. So I fit that one, telling it to stop at 13 lags, and here are the points, and they're pretty close. They kind of overlap. They're pretty much overplotting the red. There's not much difference, right? So adding those extra 6 parameters doesn't seem to change the predictions too much. If you do a scatter plot of predictions under the 2 models, they're not too much different. If you look at the models, the coefficients between the two models, most of the first order, the lower level coefficients are quite similar. This model is just, simpler. And if it does almost as well, maybe that's good enough. The one other way that time series goes, it says AR, there's a moving average, there's some other variations on that type of model. But another way time series goes, which is beyond what we'll do, is switch to the frequency domain. Switch to sine and cosine modeling. Saying there's sine and cosine, but once you take out the main trend, looking at the residuals, if they're going up and down, that's kind of a sine cosine pattern. So maybe you can choose the period, how wide that is, right? Adjust the period, scale 2 pi to get clear around the circle, right? And change the amplitude of these things and match up to your thing. So I can set up a sine curve and a cosine curve to go up and down on a yearly cycle, right? So this little command, it took me a little while to work that out, but so in 1 year, I want to go 2 pi, right? So I'm going to take pi. In R, we'll just give you the digits of pi, right? So a sequence going from 2 to 24 by 2. So it's going 2, 4, 8, and dividing by 12. So, and when it's 24, it's at 2, right? So after 12 months, I'm at 2 pi. At 12, I'm at 1 pi, and so on like that. And then I'm taking the sine or cosine of those angles, and I'm repeating that for 39, because there's 39 years in the data set. So I set up my sine and cosine. Let's look at what those look like. Here's the plot of sine. Here's the plot of cosine in orange overlaid. You can't see anything there, so let's do just 12. Right, here's 1 year. That's sine. Here's cosine for a year. And that little pattern is repeated 39 times in there. You can add text, so here's would be pi over 2 and pi and 3 pi over 2 and 2 pi for that. Here's the 0 line comparison. So we could predict the residuals based on sine and cosine functions, right? You can make predictions like that, right? So we've taken out the main trend, right? And so now it's just the random seasonal variation that's there. And if we do that, we get a summary where sine and cosine are very significant predictors, different coefficients on there, kind of like different magnitudes. They are just adjust to whatever the data are. Right? That gives an R squared of 0.87 of the residual. So we had 0.9 something just from the time trend. That was predicted pretty well. And these residuals are predicted pretty well. We could do a time series plot of the residuals. They go like that. And we could fit it into the sine cosine model on this. Does it match up pretty well? Well, it's a little bit different in places. It's kind of pulled back a little bit, maybe not quite as high in amplitude. But it overlays. And you can't see it too well there, so let's do just 3 years of it. Right? There's 3 years. There's residuals for 3 years. Here's the predicted for 3 years. Right? Smoother sine cosine. Right? It is discrete, right? By month, right? So it's getting kind of a nice representation of that. And we only have sine cosine, so two variables, right? Instead of 13 for the AR model. There's other functionality available because this is so important in environment and economics and probably other areas as well. There's a whole nother field. You could be a time series expert and just do those type of models. There's something called a fast Fourier transform that converts from the time domain to the frequency domain and back, and people that work in that get this special language of these transformations going back and forth for things. You compute things in one domain and take it back to the other one, and so on. But we don't do too much of that with the homework. The homework has you look at a few things, but that is kind of a glimpse of kind of the neat things that you can actually do with some of these variables. Any questions about it? All right, so have a good weekend. See how much more snow comes.
I didn't finish it.
through Wednesday.
Did most of it though. Yeah. I was at work when I was doing it. I showed it. So I second that. Finish it tonight.
ask like a little more actually about like I'm confused about the residual plots in terms
Yeah.
of like I don't know, like what are we looking for and like what is the difference between the ACF residual plot and the partial?
The partial one. So the ACF looks at kind of the covariance between residuals at the current one versus, you know, one time ago, or 2 times ago, or 3 times ago, or 4 times ago. And that divided by an estimate of the variance
Okay.
of the residuals.
All right.
And so if there's a big dependence at time 1, that will cause a dependence at time 2 and time 3 and things like that, because, you know, if the next one is highly dependent on this one, and then that one's dependent on this one, then over 2 lags, it's still pretty highly dependent. And
So we would
on.
get a large R1, right, and then we'd get rather like
Yeah, kind of gradually decreasing.
but so it wouldn't drop off like right towards 0 is what you're
Right.
saying. So like when we get patterns where the first R1's pretty significant, it's like say it's like significantly like 0.6 or like higher or something like that, and then we get something that's like only like 0.3, it's not like dropping all the way to 0. That signifies like this is probably autoregressive and it's like
Probably maybe order 1 autoregressive,
Yeah.
but really it's just the dependence on the previous time one that's important. And once you model that, you understand the structure of what's going on, right? So if there's an alpha at the first time, so one way to write it might be something like, you know, so if the y sub t is this alpha, kind of, you know, this thing minus the mean, right? And then t minus 1 minus the mean, then y sub t minus 1 minus its mean would be the y sub t minus 2 minus its mean. And so, you know, putting those 2 together, this one, there's like an alpha, and this thing is an alpha, so there's like an alpha squared, so y sub t minus 2 times this, and so on. So if alpha is, you know, 0.8, then this would be 0.64, and then, so it kind of decreases.
Okay.
So the expanded model would say that we get kind of an alpha 1 times y sub t1 minus b plus alpha 2 times y sub t2 minus b, and so on. You can have extra coefficients that have a different impact. Right? So they wouldn't be determined by this particular relationship. So you could have 2 large coefficients, like 0.8, 0.7, and then it goes to 0 or something like that.
Okay.
Rather than have this. So the partial one will kind of discount the second one. That it will take the residuals and then there won't be anything left over.
Okay.
And then it will give you a 0 for the partial.
So for the partial, R1's even is the most important.
Yeah,
Is it
R1,
more
yeah.
important than it is for the right.
The R1 with the partial is still R1. It's still the
Yeah.
same. But once you take out the effect of the first one, then the second partial, or the third or the fourth, those can drop off to 0
Yeah.
if it's only going through the first. Right? If the first is determining everything by succession. Then the partial, then this one would be 0 in terms of the model. You wouldn't need it.
Okay. So just kind of summarize, make sure I'm getting it. So in terms of whether we're finding whether something's autocorrelated, the most important thing is that R1 coefficient, that first residual. And then the difference between the partial and the regular is the partial, it doesn't depend as much on the first one, and like, or is that accurate?
Well, the first one can still be important, but if there's more